Okay, folks, as promised, we're now going to get into something called a temperature composition diagram, which actually describes the physical chemistry of fractional distillation. So that's pretty neat, I think. So now in our temperature composition diagram, note that these are different than our binary vapor pressure composition diagrams, where instead of having pressure on the y-axis, we now have temperature. And correspondingly, we still have composition, so mole fraction, on the x-axis. But now what I want you to recognize about this is the vapor and the liquid line are flipped in the temperature composition diagram. So in the pressure composition diagram, the liquid line was on top. Now just keep track of that. Now the liquid line is on the bottom. So I like to kind of draw a picture of a little distillation apparatus so that we can imagine what's going on in this graph. So we've got A and B in some type of boiling flask, right? And on top of that boiling flask, we connect what's known as a fractionating column, right? Where it's got all of these different like glass beads in here. Hopefully you guys remember what a fractionating column is from your organic chemistry. And then now we start boiling this mixture. So this is my really terrible drawing of a flame. Okay, we're boiling the mixture. So now suppose A and B was at this initial composition, and when we boil it, we're now going straight up to this line, so we haven't changed the composition in the liquid, right? Keep track of that. That's the boiling temperature of the liquid. However, we still get this notion of a tie line, right? And so all of that vapor that's evaporating will be enriched in A. So whatever stuff evaporates actually has this vapor composition way out there, okay? So now as that vapor goes through and condenses, and our little sidearm here, right? Remember these things? There's this little flask. This is an expert drawing, right? Where we have water coming in and water coming out. So now A and B will condense, but it will be much more enriched in A. And as it condenses on this column, right, it will condense and now have this composition. So you can see that we've actually made more A in the liquid. Well, as it turns out, the rationale for having all of these different glass beads is now we'll have multiple cycles of condensation, evaporation. And that's going to have us zigzag all through this curve, right? So now let's suppose before it's gotten up here, some of that A has condensed and then re-evaporated. So it's going to keep following these tie lines, right? And it's going to keep doing that until we've more or less gotten pure A. So if we didn't have any of those like glass beads in our fractionating column, we would have to do this over and over and over again, right? So now the liquid comes over into our another apparatus there, and now it's become pure A. So all of these glass beads will have these multiple evaporation condensation cycles such that eventually we will have separated A completely from B. So if we look at a realistic diagram here, so this is a mixture of hexane and heptane. And again, this is still a temperature composition diagram where the liquid composition is on the bottom and the vapor composition is on the top. But now we can see the curve is flipped because the hexane in this case, so that's mole fraction of heptane, right? So that is pure heptane. That would be pure hexane. So from this we can see hexane boils at a lower temperature than heptane, which makes good sense because this is a C6, this is a C7, so it makes perfect sense that it would boil at a slightly lower temperature, or pretty significantly lower temperature. But now the way that we typically use this in a laboratory is that if we wanted to extract information from this, we would boil this solution and keep track of the temperature of that vapor mixture at the top of the distillation flask, right? I don't know if you guys remember that, but you would also place a little thermometer right in the top of that. So that is a thermometer, which is going to give us the vapor temperatures. We could also have a thermometer in the liquid mixture to get those temperatures. And by recording values at different liquid compositions, right? Those liquid compositions we physically do, like we would have put those into the mixture. That now allows us to look at these tie lines and get what the calculated vapor composition will be. And you can see here, these are empirical equations that we would put there to allow us to predict vapor liquid compositions, or really boiling temperatures for any vapor liquid composition. Okay, so that's all that I want to say about that. And I just want you to remember that in the temperature composition diagram, the liquid line is on the bottom, the vapor line is on the top, but on the pressure composition, it's flipped. Okay, one more short learning goal for this module, and then we'll be done. I'll see you then.